Good morning. I'd like to talk about novel optical fibers for high-capacity transmission systems. First, I'd like to thank the workshop organizer for inviting me here. It's been a very interesting workshop so far. I think everyone has the capacity slides in different form. This is just a collection of the hero experiments at OFC and ECOG. What we can see here is, in the last few years, for single model, a single core fiber transmission, the growth kind of slowed down. Now we start to see the space division multiplexing, as there are 3 talks in this workshop already on the space division multiplexing, using either field multi-fiber or multicore fiber. Now we start to see the hero experiments in this area. So it's Nicola mentioned that we have explored basically almost every dimension of the single fiber transmission, including the pulse rate, modulation format, and then the WDM, and also polarization multiplexing. So they're pretty much close to the fundamental limit. Now, let's add a new dimension, called space division multiplexing. I think this is not really new. If you look at the a fiber cable, you have several hundreds. Some cable have 1,000 fibers there. That's a fiber bundle. Is a form of space division multiplexing. But this in the single fiber, that's really fascinating. Very good physics and research work. I think one reason we like to doing this is just keep us busy. Otherwise we'll run out of work to do, right? So I'm going to mention quickly, in terms of a single fiber. Now, what is left we can still do, because now with the advanced coherent detection technology, fiber parameters such as dispersion, PMD, are not important anymore. The only 2 parameters important is the fiber attenuation and the effective area. This a diagram showing the figure of merit. If you decrease the fiber attenuation and increase the fiber effective area, so the goal we want to move up, as the arrow point out. We want to increase the fiber effective area and decrease the fiber attenuation. So you see there is like a step change. This is because the loss limit for germanium doped core is about 0.178 dB per kilometer. Below that level, we have to use pure silica core. For pure silica core fiber, the nonlinear nonlinear index is different. This is why you see a sudden drop there. So what you can see in this diagram is when we decrease the fiber attenuation and increase the fiber effective area, the figure of merit increases. And now, we can make fiber with attenuation very close to the theoretical limit. Now currently we have a commercial fiber now called EX2000 with average attenuation around 0.16 and the effective area about 120. And we have a new product, EX3000, with similar attenuation but larger effective area. So what you can see here is reducing the attenuation is an effective way to increase the figure of merit. Increasing effective area is another approach, but there's also a fundamental limit. If you want to use a single mode fiber, the limit is about 150. Beyond that, you're going to have a micro-bending and other bending issue, which are going to increase your fiber attenuation. So, in order to make a low-loss fiber, you have to engineer the fiber material design very carefully, to achieve the fiber intrinsic loss. As I mentioned, when the effective area become larger, then you have other factors affecting the fiber attenuation. So below effective area about 115, we can achieve the fiber intrinsic loss value. If we increase the effective area, then we have to use the advanced coating, fiber coating, to reduce the micro-bending effect. As you can see here, if we we have now advanced the coating formula. Now we can achieve the same attenuation with a larger effective area. I just want to show a quick example of using this ultra low loss fiber for transmission. This work was done by in collaboration with NEC. NEC, in this experiment, we use two ultra low loss fibers. The first one is about 150 micron squared effective area. The second one is about 112. Both fiber had a similar attenuation of 0.16 dB per kilometer. So this is the transmission results. So we showed the total 11.5 terabit per second over a distance of over 10,000 kilometers, which really show you can go longer distance with this ultra low loss fiber. Now let me switch gear, talk about space division multiplexing. First, the field mode fiber. So for field mode fiber, I think there are two applications. One is the space division multiplexing, in which you use each mode as a separate transmission channel. Another application, actually, I think this application we can use now with current transmission system. We just use the fundamental mode. Use the fundamental mode for transmission. The nice thing about field mode fiber design that you can make the fundamental mode effective area much larger. Beyond the 150 micron squared limit, as I just mentioned. You can make effective area, for example, over 200, maybe is possible over 300. So let's look at the design. For design of field mode fiber, basically there are two design the concept. One is the step index. The other is we call gradient index, or the alpha profile. So if we compare the two design in terms of mode coupling, mode delay, MPI, multipass interference, or bending loss. So we can conclude that the the gradient index has advantages in terms of mod coupling, mod delay, and MPI. So overall, gradient index offers a better design. And so let's look at the group delay effect. So using an alpha profile design, if you choose the right alpha value, you can minimize the group delay, as shown here. For 1550, the optimum alpha value is about the 1.97. Yeah. With this value, you can have a nearly zero mod group delay. And so with this optimum value, you can have a wide window as well with low delay, as shown here, that you can have the delay, low delay in the whole WDM window, which is suitable, for both C and L band transmission. Now, just show one example of a few mod design. This show actual profile, fiber profile we made, and in this fiber there is two modes, LP01 and LP11, and both mode have a large effective area. Fundamental mode is 205, and LP1 is 280. Yeah. And the delay is not perfect yet, but it's very low. In the whole C band, the delay is between minus 25 to minus 2 picosecond per kilometer, which is very good. Yeah. So for field mode transmission, another important component is the fiber amplifier. We need to design a field mode amplifier to work with a field mode transmission fiber. If you use a conventional step index, design, what happens? The two modes they're going to have a different gain, so which is not desirable for the transmission. What we did, we modified this design by adding a ring structure around the core. In this way, we can equalize the gain for the two modes, as shown here. Okay, so using the transmission fiber and the EDFA fiber, again, we did an experiment in collaboration with NEC. This is the experimental diagram. We have 50 kilometer field multi-fiber together with field mode EDFA. In the experiment, we use WSS, which allowed us to choose the wavelength band. We can choose either a wide band or a narrow band. Yeah. For the wide band, we had 146 wavelength channels. Then we demonstrated 500 kilometer transmission, 500 kilometer the total length, and the limitation is the amplifier gain flatness. Because we didn't have a gain flattening filter in the experiment. Then we narrowed the wavelength band, to choose only 16 channels. In this case, we managed to go about 1,000 kilometers, for which I believe this is the longest distance for field mode transmission. Now, let me talk about the multicore fiber. So for multicore fiber, we can have different designs. For example, you can have a hexagonal design, which offers the high packing density. or you can have linear design, linear array. I think the linear array are interesting for short range applications because you can adapt to linear laser arrays. This is one fiber, 14-core fiber we made, which has 12 single modal cores, and there are 2 field modal cores. So we wanted to show both the multi-core, the transmission and the field modal transmission in the same fiber. So again, we did a transmission experiment with NEC, using this the 14-core fiber. Yeah. This is the experiment diagram, and which I'm not going to explain in detail. I just want to show the result. So the experiment showed a record of 1.05 petabit per second transmission, and with a spectral efficiency of 110. Both set a new record. So what can you do with 1 petabit? This how much information you can transmit. Yeah. Okay, so now very quickly I'm going to show the multi-core fiber for short reach application. I think for short reach application, the nice thing is you don't need amplifier, right? You don't need a fan-out device if you can adapt to the laser array directly. Yeah. This the 2 pictures showing one 1x4 fiber we made, and the other one is a 2x4. And this crosstalk measurement on 2x4 fiber, the crosstalk basically is very low. Of course it depends on the wavelengths, but they're all below minus 45 dB. Yeah. And we did a transmission experiment using this 8-core fiber. Because distance is very short, 200 meter, basically you don't see any penalty there. Yeah, if you look at the eye diagrams, they're wide open. Yeah. Okay, that's come to the end of my talk. I think space division multiplexing is very interesting, but there are significant challenges in before it becomes a practical application. First is the fiber. From a fiber point of view, we want to understand better, the design space, and also the develop low-cost manufacturing process. And I think the more challenges in terms of components. I think NEC has mentioned many components already. Yeah. I think another interesting, very important thing is integration. Without integration, I don't think you can have a value proposition for space division multiplexing. Thank you very much. You're talking about multi-core amplifier. Yeah. Okay. We have not done any work in the multi-core amplifier, but there are publications talk about multi-core amplifier. Multi-core amplifier. I think there are a lot of challenges there too. So you have to make every core the gain. The equalize, that's not easy to do.